All right, let's just jump right into this explainer. Today, we're zooming in on a really foundational physical science topic, and it's honestly a fascinating one. We are going to explore the whole world of matter, how it transforms from one state to another, and finally, we'll clear up a really common misconception that trips up a lot of us: the big difference between temperature and heat energy. If you've ever stopped to wonder why ice melts, how balloons actually inflate, or why a boiling pot of water is way more dangerous than a single boiling drop, well, you are definitely in the right place.
So here is our roadmap for today's explainer. 1. Meet the particles. 2. Solids, liquids, and gases. 3. Tracing phase changes. 4. Temperature versus energy transfer. And 5. A quick recap and transfer question. Let's get to it.
Section 1. Meet the particles. We have to start by asking, what exactly is matter?
To answer what makes up literally the entire universe, we have to define matter. And it's pretty simple. Matter is anything that occupies space and has mass. The really crucial takeaway here is that whether it's a heavy, solid textbook sitting on your desk or the completely invisible air trapped inside a helium balloon, if it takes up physical space and has mass, no matter how tiny, it's matter. It's the actual physical stuff of our universe. Now, as you probably know, matter doesn't just exist in one single boring form. It takes on different states. And yeah, while there is a fourth state called plasma, which is full of electrically charged particles and is found in wild stuff like stars and lightning strikes, the three states you see right here, solids, liquids, and gases, those are the primary states of matter we interact with every single day here on Earth.
Moving to Section 2, solids, liquids, and gases. Let's look at the particle model.
What's really interesting is what happens when we zoom way in to look at the particle model. In a solid, those particles are tightly jammed together with very little movement. They essentially just kind of vibrate in place. That's exactly why a solid is rigid and holds a definite shape and volume. Now, in a liquid, the particles have a little bit more energy, right? They can actually slide past one another, and because they flow, a liquid takes the shape of its container, but it still maintains a definite volume. Finally, gas particles have so much energy that they move freely and super rapidly, expanding completely to take on both the shape and the total volume of whatever is holding them.
But, sometimes our eyes can play tricks on us based on how things behave on a macro level. Take sand, for instance. You can easily pour sand out of a bucket just like water. So, is it a liquid? Well, actually, no. As you can see here, even though it pours like a liquid, sand is really just composed of thousands of tiny individual grains of solid matter that are acting together. Each individual grain is totally rigid and holds its own definite shape.
All right, it is time for our first pause check. I want you to actively apply what we just covered. Thinking about the particle model of a gas, why does a completely flat balloon inflate and expand when you blow air into it? Take just a second to think about your answer before we reveal the science behind it.
Okay, got it? Here's the answer. Even though we often can't actually see gases with our naked eye, they are absolutely matter. When you blow air into a balloon, you are literally pushing millions of freely moving gas particles right into that enclosed space. Because gas particles expand to fill their container, and because matter by definition has to take up space, that gas pushes against the inside of the balloon and increases its volume. Literally, if gases didn't take up space, that balloon would stay completely flat.
Up next is Section 3, Tracing the phase changes. Let's walk the energy staircase. So we know how particles act in each state, but what happens when we crank up the heat or cool them way down? Well, we get a physical change. This is a change in the state or properties of matter without any change to its actual chemical identity. This part is vital. When solid ice melts into liquid water and then boils into gaseous steam, the molecules themselves are always H2O. The particles simply change how much energy they have and how they physically arrange themselves.
You can imagine this like a literal energy staircase. Walking up the staircase means we're adding heat energy. Down at the bottom step, where we have the lowest energy, we have a rigid solid. As we add heat, we're giving those particles more energy to break away from their tight bonds. That's melting, which takes us up to the liquid step. If we just keep adding heat, the particles gain even more energy, eventually boiling or evaporating, breaking free entirely to become a freely moving gas at the very top of our staircase.
On the flip side, we can easily walk back down those stairs by removing energy, which we experience as cooling. When a highly energetic gas loses heat, its particles slow down and bunch closer together in a process called condensation, turning into a liquid. Remove even more heat and the particles slow down so much they lock right back into a rigid structure. We call this freezing.
And again, through this entire up and down journey, the chemical composition remains 100% unchanged.
Our source material actually hits the nail on the head with this quote, reminding us that we aren't just talking about abstract science lab concepts here. These physical changes are happening all around us in our everyday lives. Melting candle wax or steam condensing on your bathroom mirror after a hot shower. These are all super visible, everyday examples of particles walking up and down that exact energy staircase. Moving on to Section 4, temperature versus energy transfer, intensive versus extensive properties.
Okay, so right here is a classic stumbling block. It is so easy to assume temperature and heat energy are the exact same thing. But to explain why they're distinct, we need two new terms. The first is an intensive property. This is a property of matter that does not depend on the amount of matter present. Temperature is a perfect example of this. Think about it. A tiny teacup of boiling water and a massive industrial vat of boiling water are both sitting at exactly 100 degrees Celsius. The temperature honestly doesn't care how much water is actually there.
But then we have the extensive property. This is a property that depends directly on the total amount of matter present. Mass and volume are obvious extensive properties, like 2 gallons of milk obviously take up more volume than 1. But here's the kicker. Total heat energy is also an extensive property. That means the total amount of thermal energy contained in a substance depends heavily on just how much of that substance you actually have. This comparison illustrates the difference in a really practical and kind of painful way. Let's compare a single tiny drop of hot cooking oil spattering on your arm versus spilling an entire large pot of hot cooking oil on yourself. Both the drop and the pot of oil are at the exact same intensive temperature, but the pot contains vastly more matter, which means it contains a massively larger amount of extensive heat energy. That total energy transfer is what causes severe, dangerous burns, compared to just a brief sting from the single drop.
All right, time for our second pause check. Let's really test your grasp of intensive versus extensive properties here. If you have a full gallon of milk sitting at room temperature, say 20 degrees Celsius, and you pour in a cup of milk that is also at 20 degrees Celsius, what is the new temperature of all that combined milk? Have your answer ready.
And the answer is, it stays right at 20 degrees Celsius. Because temperature is an intensive property, remember, it does not depend on the total volume. You absolutely don't add the temperatures together to get 40 degrees. The volume and mass increased extensively, sure, but the intensive temperature remained exactly the same.
And finally, Section 5, quick recap and transfer, tying it all together.
Let's just zoom back out and wrap up this explainer. To summarize our journey today, we established that matter occupies space and has mass, existing as solids, liquids, and gases depending on how much their particles are moving. We saw that heating and cooling cause physical phase changes, basically walking particles up and down an energy staircase without ever changing their core chemical identity. And finally, we learned that temperature is an intensive property independent of amount, while total heat energy is an extensive property completely dependent on how much matter is actually present.
I'm going to leave you with one final transfer question to chew on. Imagine a small, single-lit match at a massive, raging bonfire. Let's say the flames of both are burning at the exact same intensive temperature. Based on what you've learned today, which one contains more extensive heat energy and why? Really think about the particle model and the amount of matter involved there. Thank you so much for exploring physical science with us today. Keep asking those great questions, and I'll catch you in the next explainer.